On the 18th of February, 2025, a rock you'd never heard of quietly became the most dangerous object humanity had ever tracked. Its name was 2024 YR4. It was about the width of a football field, and a NASA system had just put the odds of it slamming into Earth in December 2032 at 3.1%. That doesn't sound like much, but no asteroid that big had ever climbed that high on the risk scale in the entire history of asteroid tracking. 1 in 32, roughly the odds of rolling a specific number on 2 dice, against a city. For a few weeks, planetary defense teams on 2 continents watched that number with their stomachs in knots because they knew exactly what a rock that size could do. And then something strange happened. As telescopes pinned down its path, the odds didn't just fall, they jumped off the Earth entirely and onto the Moon. By mid-2025, the question had flipped to will it hit the Moon instead? 4.3%. Then, after one last faint look from the most powerful telescope ever built, even that vanished. In March 2026, the all clear. It misses both. That whole roller coaster, the panic, the jump to the Moon, the all clear, was a fire drill, a real one. And it forced the question this whole video is about. If that number had stayed at 3%, or climbed to 30, or to 100, could we actually do anything? Or do we just look up and wait? Let's deal with the thing nobody likes to say out loud first. How bad is it, really, when one of these hits? You don't need a dinosaur killer to ruin a city. On the 15th of February 2013, by pure coincidence, the same day a different, larger asteroid was making a long-predicted close pass. A rock about 20 meters across came in over Chelyabinsk, Russia. It never even hit the ground. It exploded in the air, roughly 19 to 24 kilometers up, with the energy of around 30 Hiroshima bombs. The flash was brighter than the sun. The shockwave shattered windows across 6 cities and injured around 1,500 people, most of them because they'd run to their windows to see the brilliant light, and the glass blew in on them seconds later. 20 meters. And here's the part that should bother you. Nobody saw it coming. The warning time was exactly 0. It came out of the direction of the sun, where our telescopes are blind. Now scale up. In 1908, something, most likely a stony asteroid somewhere around 50 to 60 meters wide, exploded over Tunguska in remote Siberia. It flattened around 2,000 square kilometers of forest. 80 million trees knocked down in a radial pattern pointing away from the blast. If that had arrived a few hours later, with Earth's rotation, it could have erased a major city. That's the size class of 2024 YR4, the rock that just gave us the scare. Not an extinction event, a lose a metropolitan area event. Those are the ones we actually have to worry about, because they're far more common than the giant ones, and far easier to miss. And here's how seriously we take these things. We name the scary ones after gods of destruction. In 2004, astronomers found a 370-meter asteroid that early data suggested might hit Earth in 2029. They named it Apophis, after the Egyptian god of chaos. Later observations cleared it. It will not hit us, but it is still coming. On the 13th of April, 2029, Apophis will pass just 32,000 kilometers above Earth's surface, closer than the ring of geostationary satellites we depend on every day. A rock the size of a cruise ship, skimming beneath our own spacecraft. It will be visible to the naked eye to something like 2 billion people across Europe, Africa, and Asia. A bright, moving star. The first time in recorded history we'll watch an asteroid this size sail past on purpose, knowing in advance it's coming. Let that recalibrate your sense of how close can get. Which brings us to the first and most important weapon in the whole arsenal, and it's not a rocket. It's time. Every method of stopping an asteroid, every single one, runs on advance warning. Find a threat 10 years out and you have options. Find it 10 days out and you have prayers. The entire game is detection. And right now, our detection has a giant hole in it, the direction of the sun. Telescopes work at night, looking away from the sun, which means anything approaching from the daytime sky, like the Chelyabinsk rock, is essentially invisible until it's on top of us. To plug that hole, NASA is building a dedicated space telescope called NEO Surveyor, designed to hunt these objects in infrared from a vantage point where it can stare closer to the sun. The target is to find 2/3 of the dangerous mid-size asteroids within 5 years of operation, finally chipping away at a job Congress ordered decades ago: find 90% of the city killers. The launch is targeted for around 2027. Until it's flying, we are, in a real sense, partly blind. So say we do find one early. We've got 15 years of warning. Now what? Here's the good news. We are not guessing anymore. We've actually done this. In September 2022, NASA flew a spacecraft the size of a vending machine called DART straight into an asteroid, on purpose, at roughly 22,000 kilometers an hour. The target was a small moonlet named Dimorphos, about 170 meters across, orbiting a bigger asteroid. Crucially, neither was any threat to Earth. This was a test on a live target, where we could measure the result from the ground. The idea is brutally simple. Hit the rock hard enough, early enough, and you nudge its speed by a tiny amount. Over years, that tiny nudge compounds into a miss of thousands of kilometers. You're not blowing it up. You're changing its arrival time so that when it crosses Earth's orbit, Earth simply isn't there yet. Before impact, Dimorphos circled its partner every 11 hours and 55 minutes. The mission would have been declared a success if DART changed that by just 73 seconds. The actual result? 33 minutes. The little spacecraft shortened the orbit by more than 30 minutes, wildly beyond the bar. And the reason why is the most interesting part. DART's own mass barely mattered. The real punch came from the spray. The impact blasted a huge plume of rock off the asteroid, and all that debris rocketing into space acted like a second engine, roughly doubling the push. Scientists call it the momentum enhancement factor, and for DART, it was about 2. The ejecta tail that formed stretched over 70,000 kilometers into space. We didn't just tap the asteroid kicked back in our favor. But there's a humbling footnote to that triumph. We hit Dimorphos so hard, we may have reshaped it, turning that neat, squashed sphere into something more like a lopsided lump, and we still don't precisely know its mass, which means we don't precisely know how efficient our own punch really was. To find out, Europe launched a follow-up spacecraft called Hera in October 2024. Right now, as you watch this, Hera is in deep space, closing in on Didymos and Dimorphos, due to arrive at the end of 2026 to survey the crater we made and finally measure what we actually did. Think about what that means. We already took the shot. We're only now flying out to read the scorecard. That's how new this all is. So that's method 1, the kinetic impactor. Hit it. Proven, flown, it works. But it has a catch. You can't fully predict how much a given rock will spray, and hit something too small or too loosely held together too hard, and you risk shattering it into a shotgun blast of smaller pieces instead of cleanly nudging one. Sometimes you don't want a sledgehammer. Sometimes you want tweezers. That's where method 2 comes in, and it's almost absurdly elegant. The gravity tractor. You don't touch the asteroid at all. You park a heavy spacecraft a short distance off its surface and just hover there. The faint gravitational attraction between the two, the same force that holds you to the ground, but whisper quiet at this scale, gently tugs the asteroid toward the spacecraft. The craft fires its thrusters outward, angled so the exhaust doesn't blow on the rock, holding its position for months or years, and the asteroid follows it like a balloon drawn toward a hand it never quite touches. The beauty is total control and zero risk of breaking the thing apart. You don't need to know what it's made of, how it's shaped, or how it spins. In fact, the concept was first worked out by NASA scientists with a specific target in mind: Apophis, that same god of chaos rock, as a way it could have been gently towed off a collision course if the early scary numbers had held. The downside is it's slow and weak, so it only works with lots of lead time, which loops us right back to the real currency here. Warning. Method 3 is the same philosophy with more muscle: the ion beam. Instead of using the spacecraft's own gravity, you point a stream of high-speed ions, essentially a focused thruster, directly at the asteroid, pushing it continuously without ever making contact. Gentle, precise, no fragmentation risk, and the force doesn't even depend on the asteroid's size. Again, slow, steady, needs years. Notice the pattern. Almost every safe method is a slow push. Time is the thing that makes them possible. And then there's the one everyone asks about. The nuke, the Hollywood option. Here's the reality, and it's not what the movies show. The plan was never to land on it, drill a hole, and blow it into chunks raining down on Earth. That's about the worst thing you could do. The actual concept is a standoff burst. Detonate a nuclear device near the asteroid, not on it. The blast floods one side with radiation, instantly vaporizing a thin layer of the surface. That vaporized rock blows off into space like a sudden rocket exhaust, and the recoil shoves the entire asteroid the other way, intact. It's the kinetic impactor idea, but with vastly more energy, reserved for the nightmare scenario. A rock too big to nudge, or one found too late, where you need a huge velocity change fast. It's the last resort, the break glass option. And notably, it's the only method on this list we have never actually tested in space. So line them up. A telescope to see it coming. A sledgehammer for the standard case. Tested. Works. Tweezers in 2 flavors for when you have time and need precision. And a nuclear Hail Mary for the day we get unlucky. On paper, humanity is the first species in the history of this planet that can actually do something about the rock with its name on it. The dinosaurs had no space program, but every single one of those tools is useless without the one resource we can't manufacture: lead time. And that's the uncomfortable truth the 2024 YR4 drill exposed. We found that rock in late December 2024, and we only spotted it 2 days after it had already made its close pass because it came at us from the sun's direction. Its possible impact was 2032. That's a comfortable margin, but Chelyabinsk's warning was 0. If a Tunguska-sized rock came out of the daytime sky tomorrow with our current eyes, we would not stop it. We'd evacuate if we were lucky enough to even get that. So the honest answer to, can we stop an asteroid, is yes. The physics is solved. The hardware is proven. We have literally moved one. The answer to, do we have enough time, is the one still being written, telescope by telescope, in the years before the rock with our name on it actually shows up. We are, right now, in this strange and narrow window where we've built the deflectors but haven't finished building the eyes. The asteroid that ends a city isn't a question of if, it's when, and whether we're looking the right way when it comes. 2024 YR4 missed. The next one might not announce itself 2 days late from the glare of the sun. It might not announce itself at all.